5.1 approximating areas. So finding the area of a particular shape is a rather difficult problem in general, which is made a lot simpler through calculus, especially when it's not a regular polygonal shape that we're all familiar with. It has some sort of formula, like we know the area of a rectangle is length times width. We know the area of a circle is pi r squared and things like that. But if it's a non-standard shape, like for instance the area under a function, right, some smooth curve, okay, that can be a lot more difficult to try to compute. So I'm going to take a function. I'm going to take x squared. I'll try to draw it here. We're going to find the area. Between f of x equals x squared and the x-axis along the interval 0 to 2. Okay. Now when I say find the area, we won't be able to find the exact area here. We're just approximating. This question there'll be a main focus for the rest of chapter 5. We'll try to attain the exact area soon enough. But just to start this whole idea off by approximating areas. All right, so if I draw from 0 to 2, I'll scale the x-axis in such a way I can see a little bit more here. So let's just say that, just do it like this. We'll call this 0.5. Call this 1. This will be 0.75. Sorry, this will be 1.5. And I'll extend this just a little bit further. You get 2 in there. Okay. 2. But here I'm not going to exaggerate. I'm not going to have such a large scale for the y-axis. So let's make it 1, 2, 3, 4, something like that. Okay, so we know that at 1 it should be up here at 1. Right, it's x squared. So we know 0, 0, 1, 1, and we know 2, 4. So I should draw some sort of parabolic looking thing through here. Again, all this is slightly exaggerated, and it's kind of like you're zooming in on this part of the curve, just so I can demonstrate the process we're trying to look at here. Okay, so there's our function from 0 to 2 is all we really need. 2, 4 over here. Origin down here, and 1, 1, as we know would be on this function x squared. Great. So one of the ways we're going to approximate the area between this curve and the x-axis, right? We're really trying to find, what we'd like to find, but we'll not be able to at this moment, is this area here, right? All this. We would like to know the value of this wedge, you might say. Although it's triangular looking in some sense, of course it's not a triangle, right? We know this is a curve, right? It's not a line here. So we're going to find this area, get a good approximate for this area right now, and lead our way into finding the exact value of this area. Which again is a challenging question, especially before calculus. Because there's the area we want to get a handle on. We'll do this by using the formula, a very simple formula for areas that we know before, which is the area of rectangles. So we're going to use rectangles to find these areas. Okay, so we're going to use what are called approximating rectangles. And the main reason is because we know the formula for such a thing is length times width. To approximate the area under the curve. Okay. All right. So I'm going to choose a certain number of rectangles. I'm going to choose 4 rectangles. Okay, that's my choice. The problems in the text will probably tell you how many to choose or how many to use. So I'm going to say n, that's the number of rectangles in these types of formula that we're going to produce here. So n equals 4 rectangles. I'm going to use 4 just for my example here.